Hello everybody. So this video is a continuation of the example problem that we were working on in the last video. So this is part 2 of a few videos. So if you haven't watched part 1 yet, go back and watch that first. But if you have watched part 1, here's the continuation. Your reminder is that we're looking at a gas that was initially 3 cubic meters inside of a cylinder at standard temperature and pressure. It got compressed, the pressure rose, the temperature rose, and in the last video, we looked at this quantitatively accurate LOL diagram uh, for the gas before and after. This video is going to be looking at the energy transfer processes that occur to make it so that we can have more energy at B than at A. So between the pictures, we want to draw an accurate PV graph for this process. We want to use it to determine the amount of work or amount of energy that's transferred through a working process. So that's where we're at. Let's stop and think first, though. The gas compresses. What that means is that we know that the work is being done on the system by the surroundings. So in other words, the surroundings outside of our system is compressing that gas, is pushing on the cylinder harder and winning that fight. So energy is entering into our system through a working process. Thus, we expect a positive work value. So we want to make sure that we get a positive value in the end. Now, here's our picture from before. This could work. This could explain everything. This one extra block of energy we had in the end could come from work. So we'll draw it as one purple block pushing energy in. This might be it. Spoiler alert, we'll have to revise this picture a bit, but let's start here. Let's draw our PV diagram. PV diagram means graph pressure on the vertical axis versus volume on the horizontal axis. I'll use kilopascals for my pressure unit and cubic meters for my volume unit. State A, snapshot A. That was at the point where the volume was 3 cubic meters and the pressure was 101.3 kilopascals. So that's the point for this state. Everything in that state can be represented by this single point. Well, I guess not everything. The things that are missing are temperature and how much gas is there. But there's a lot of information on this graph here. Snapshot B was at a lower volume, so it's going to be to the left on the horizontal axis. And it was at a higher pressure, so it's going to be higher up on the vertical axis, something like that. Volume B is 0.827 cubic meters, and the pressure is 4 atmospheres or 405.2 kilopascals. Now, a key thing that is missing on this graph is time. If I didn't label those 2 points A and B, you'd have no way to know whether or not the gas started at a high volume and low pressure and then compressed and increased pressure, or the reverse could be true, right? It could have started at a smaller volume at a high pressure and then expanded out to a higher volume while decreasing in pressure. Time information is missing on this graph. What else we don't know right now, anyways, without more information, is how did we get from A to B? Did we maybe compress at a constant pressure and then increase that pressure? Or maybe we increased the pressure first at a constant volume and then we compressed the gas. Or maybe we did both at the same time. Both the compression and the pressure increase happened simultaneously, in which case it could have been some curve from A to B. And if the increase in pressure and the decrease in volume were both linear, then it might be a straight line from A to B. The point is, we don't know. And in the future, you'll be given more information on how we went from A to B. For our purposes, we will assume one of the simpler paths, which was a straight line path from A to B. And because we want to share information about the fact that we went from A to B and not B to A, we will orient this curve or give it some direction. So we'll put a direction arrow pointing from A to B. Next, let's talk about that volume change. It's a compression. So we're going from the bigger to the smaller volume. We expect the volume change to be a negative number. Let's compute it, make sure. Change in volume is defined as the volume at B minus the volume at A, final minus initial. Plug in those numbers, 0.827 cubic meters minus 3 cubic meters, and we end up with a negative 2.17 cubic meters. All right, that works out. So our volume is in fact, our volume change is in fact a negative number. Now, let's do some more thinking about this graph here. That area is what we're after. This area underneath of that curve, the negative of that area gives us the work. Just a quick reminder that when we're finding this area, we're going all the way from the curve all the way down to that horizontal axis. We're not stopping at this point here. We're going all the way down. So at a constant pressure, the work that is done is equal to negative P times delta V. This is the equation that's on the AP Physics 2 equation sheet. Now, how do we take this equation and generalize it to something that's true even when the pressure doesn't remain constant? Well, we've already talked about it, but I want to talk about how we can use this equation as a reminder if we forget later on. So this translates to the work being the negative, the area under the PV diagram. How does that work? Well, let's think. Pressure times change in volume. Well, that's kind of like area, right? Multiplying two things together gives you area. If you multiply 3 feet in one direction by 4 feet in the other, you end up with 12 square feet of an area with a rectangle, or for the area of a rectangle. If you have a calculus class, we can be a bit more precise with that, and we can say that this delta V becomes dV in the limit that delta V approaches 0, and we integrate to find that area. So negative integral of P dV gives you the work that's done for a gas. Now, we're going to use this to compute the working that's done in this process. I like to multiply this negative sign over to the other side of the equation until the very end, so I can just focus on the area portion of this, and then I'll multiply everything by -1 in the end. So, I see that this shape is a trapezoid that can be broken up into a rectangle with height PA, the pressure at state A, and then a triangle, and that triangle has height PB minus PA. That's the height of this triangle. And the sum of the area of this triangle plus the area of this rectangle will give me the area of the total shape. So write that same idea now as an equation. Pressure at A times delta V is the rectangle area, and then it's a triangle, so half base times height gives you the area for the rectangle, with the height being the difference in pressures. Plugging in some number values now. Pressure at A is 101,000. Pressure B minus pressure A is that difference. And we need to keep in mind for each of those delta V's that the pressure change is a negative pressure change because we're decreasing the volume. And so when we go ahead and plug that all into a calculator, we end up with that the negative work is negative 550,000 joules. And so multiply everything by -1, the work is a positive 550,000 joules. We expected a positive working value because the surroundings was adding energy into the system by compressing the gas, and we did end up with a positive value in the end. It can be very easy to lose track of a negative sign somewhere and get the wrong sign. So make sure you always go back, was I expecting a positive or negative value because of the compression or expansion of the gas? So you can always check yourself there. Now, what this means visually is, or what this means is that this working area we drew before should be labeled with a value of 550,000 joules. Uh-oh, we've got a problem here. This doesn't add up. We started with 456,000, added 550,000, ended up at 502,000. That seems like an issue, right? Here's another way to think about what I just said. Initial plus change equals final. That's our whole thought process here for using the first law of thermodynamics. The initial energy was that 456,000 joule value. We add in that change we just computed of 550,000 joules. Is that equal to that final value of 502,000 joules or 503,000 joules? No, that does not add up. We're missing something here. We're not done yet. Oh wait, there are two ways now that energy can be transferred, not just the one. So working was the only energy transfer process we had before, but now we have both working and heating. So we must have some energy exchange through heating. That must fix this problem. So this is where part E comes in, where we draw a quantitatively accurate system schema for the process that includes the heating that's done. And this will fix all of our issues. So first law of thermodynamics. Initial system energy plus all energy changes and flows equal your final system energy. That's the deal. Another way to say that is your initial energy plus the change that's done by work plus the change that's done by heating equals your final energy. As variables, that means U internal subscript A plus working W plus heating Q equals your internal energy at state B. We know 3 of those 4. We can figure out the 4th one. Plug in your initial energy value, your work value. If you don't know Q, your final energy value. Solve this for Q, you end up with a negative 504,000 joules. What does that negative sign mean? That's telling us that 504,000 joules of energy transfers out of the system through a heating process. So, some changes to our picture. We really should have drawn some energy leaving the system through heating, about 504,000 joules, which means that we really needed to draw this work arrow to be more blocks of energy than we initially did. Visually, what we're representing here is we started with these 2 red blocks. Those 2 red blocks left through heating, 3 purple blocks entered through working, and we ended up with those 3 purple blocks in the end. So the 2 we started with leave through heat, 3 purple enter through work, and we're end up with 3 purple in the end. Now this math all checks out. Everything works out here to be accurate. This is our final answer. We now know everything about this piston stroke. We know pressures, volumes, temperatures, number of gas particles in the initial and final states. We know the energy, the internal energy in both states, and we know the energy transfer processes that allowed us to get from initial to final. I hear you have an objection though. Here's what you're thinking right now, something that doesn't make sense. How is it that even though the system increases temperature from A to B, we're losing heat to the surroundings? The heating process flows out of the cylinder and into the surroundings. So how can we be losing heat? Backing up here, why is this Q arrow pointing out of the system even though the temperature is increasing? So I've got some animations in the next video to help you think through this a bit more, but the quick answer is this. The increase in temperature was due to the working that compressed the piston. Think back to the Veritasium video with the fire syringe, where they compressed that gas down, which increased the temperature of the gas, igniting the cotton that was inside. The temperature increase was due to the compression, not due to a heating process. So the heating was able to flow from outside of the system to the environment, to the surroundings, because the environment was colder than the system. We don't care about the fact that the system's energy or the system's temperature increased for heat flow. What we care about is the relative temperatures between the environment and the system. So even though the system's temperature increased from 0 degrees Celsius to 28 degrees Celsius, the environment must have always been colder than that 0 degrees Celsius, which is why that heating direction flow was from the system outside the system. Got some animations to help with that idea in the next video. So that's it for this video. We'll back up. Here's the final answer, talking about all of the possibilities for our state variables at state A and state B, and the flow of energy that happened between those 2 states. Stay tuned for the next video where we have an animation helping us think about the difference between temperature increase and heat flow.